Okay. All right, so now we're going to 5 to the negative 2. So yes, you can do 5 to the negative 2 in the calculator, but we can also use what we remember from before, which is 5 to the negative 2 is going to be the reciprocal of 5 to the positive 2. So what's 5 squared? 5 squared is 5 times 5, which is 25. And so the reciprocal of that is 1 over 25. Okay, so I'm going to give you guys a minute, and I want you to try to find the exponents that would give you these answers. Okay, so it's going to be 4 to some power gives you 4, 4 to some power gives you 64, and 4 to some power gives you 256. Okay, okay. So 4 to what power gives you 4? What'd you get? 1, yeah. So the 1 goes here. If you want to write it as 4 to the 1, put that out there, okay? 4 to what exponent gives you 64? S has 3. Anybody else get 3? Yeah? Okay. So 4 to the 3 is 64. And Edward, what did you get for 256? 4, good. 4 to the 4.
If it was 1, it would be 3.
All right, I'm hearing good discussions about what these could be. Remember, you can always check yourself if you're not sure with Desmos. So let's look at these first. 4 to the 1/3, that one is giving me a reciprocal. Sam, what did you get for that one? This one here. 3 to the what gives you 1/3? -1. Did anybody else get -1 for that? Good. Good. So a negative exponent is going to give you that reciprocal. And if you wanted to check that, you would do 3 to the -1 in Desmos. And then you're going to have to change that answer to a fraction. So type 3 to the -1. I get this, but if I hit the fraction over here, you can see that 3 to the -1 is 1/3. Okay? All right, what kind of exponent is going to give me 1 as my answer? S says 0, and Catherine says 0. Is that right? Yeah? Good. So 3 to the 0 gives me 1. All right, what exponent will give me 27? 3. So 3 to the 3 is 27. And then I wonder if anybody worked on this one. Raise your hand if you worked on this and you found an answer that you're happy with. Okay, I didn't expect that one to be easy, right? Because it's not an even power of 3. Like 3 to the 3 is too small, and 3 to the 4 is too big. And so in our other class, some people did a little bit of guess and check, and they found something they were happy with. You did that too, Nyla? Yeah, what'd you get?
3.4, it's like 41.
3.4 was really close. Okay, excellent. So a little bit of guess and check will get you really close. And to get the best possible answer, there's something called logarithms. So I'm trying to teach you guys the purpose of logarithms, and the purpose of logarithms is if you needed to solve a problem like this, where you said 3 to the x is some number, and it wasn't something that was easy to work backwards on. Okay? So we're going to solve it with an inverse function. If the equation was x divided by 3 equals 40.541, you would solve by multiplying, because division and multiplication are inverse functions. All right, so in Algebra 1, you learned how to solve by undoing operations with their inverse operations. You undo division with multiplication. You undo addition with what operation?
Subtraction.
With subtraction, yeah. Undo addition with subtraction. And so you undo an exponential with a logarithm. And luckily, we don't have to say the whole word logarithm. Usually we just say log, and we just write log. So you can solve 3 to the x equals 40.541 by taking the log base 3 of each side, because logarithms are the inverse of exponentials, which means they undo each other. Okay, so logarithms were invented by mathematicians to solve this problem of being able to get that x out of the exponent. However, like mathematicians, sometimes they can be kind of like exclusive and they can be kind of jerks and they can make these long words like logarithm for something that's actually really easy. Like all we're doing is undoing this exponential equation, but they're making it sound like it's a hard thing, and it's not really that hard. But it makes you sound smart because you know how to do it and other people don't. Okay? All right. So here's what we do. We do the log base 3 of both sides. See, I'm solving this problem right here. And what I did was I applied a logarithm. I did not multiply a logarithm. Some people think it looks like multiplying because it's next to each other. That's not what I did. I applied a logarithm, base 3 to both sides. The base is 3 because the base of the exponential is 3. They have to match. That will cancel out this 3 here, leaving me with just x. And then on this side, I have log base 3, 40.541. In the Desmos calculator, we're going to go into the functions menu, and it's actually not in miscellaneous. It's in the calculus menu. I told you we were doing smart things today. Okay? So we're going to go into the Desmos calculator. We're going to find the button that says functions, and we're going to scroll down to calculus, and we're going to look for log base A. This is the button that we're going to look for. Okay? So we're going to do that right now. I'm going to a new line. I'm going to click on the keyboard, functions, and I'm going to scroll down to the calculus menu, and I'm going to choose this one, log base A. Oops, you guys can't quite see that. Oh, yes, you can, right here. Choose this one, log base A. So if you were using a 4-function calculator, I need you to switch over to Desmos. And then you're going to choose this in the calculus menu. You're choosing log base A, and we're going to put in base 3. That goes down there. And then the number 40.541. All right, and so we get a few more decimal places than Nyla got with a guess and check. She gave us a really good estimate. And now we have a few more decimal places. So we can write this to 2 decimal places. We can write 3.37. Okay? Let me know if you need help, Catherine. So remember, when you go to functions and calculus, you're choosing log A, not just regular log. That way you can put in the base of 3. And then, did I say we got 3.37? Yeah.
Where is it?
Okay, I'm going to show you. We're going to do the... Okay. All right, so I'm going to start you guys on number 5, but you know how to do these now. You're going to type log, and the base of the log has to match the base of the exponential. Remember, the base is the number under the exponent. So the 4 is the number under the exponent. So I'm going to do log base 4 on both sides of the equation. Log base 4, 4 to the x, equals log base 4, 16,384. And the reason we do that is because log base 4 will cancel, and you just get x. And then you're going to type this one into your Desmos.
What was the answer? So,
All right, so we get 7 for this one. And for this whole row of problems, notice they all have a base of 4. So each one is going to be log base 4. All right, and then you're going to type in your other number. I'll do another one with you, but you guys can feel free to work ahead because you know how to do this. All right, so I did log base 4 on both sides, and then I'm going to type this in. And I got 2.5, and I would prefer to write that as a fraction. So over here, I want you to choose the fraction and make it to 5/2. So x equals, just write equals 5/2 after it. All right, do 7 and 8 right now. Okay, so what we're going to do to get this x out of the exponent is take the log base 4 of both sides. So log base 4 of 4 to the x is equal to the log base 4 of 0.125. And log base 4 of 4 to the x, the log base 4 and the 4 cancel, giving you just x. And that's the reason why we did log base 4. And then in the calculator, you're going to type this one. So I'm going to do that right now. I already have log base 4 in here, so I'm just changing this to 0.125. And it gave me the fraction, but if it didn't give me the fraction, if it gave me negative 1.5, I could change it to a fraction by hitting this one right here. So I get negative 3/2 as this answer. I appreciate your patience if you're done. That's great. This one, I'm going to do it up here because I kind of ran out of space. So the problem is 4 to the x equals 72.52. You're going to do log base 4 on both sides because the base of the exponential is 4. So whatever this number is, that's what you do for your log base. Log base 4, 4 to the x equals log base 4, 72.52. Those cancel. And this is what we type into Desmos. Now I'm going to show you, if you weren't here when we did this the first time, where to find that log base 4. Okay? So for this one, we're just going to write 3.09. All right, so did anybody figure out how to check their answers? What'd you do, Kyle?
I divided the answer with the base number the amount of time the exponents.
Wow. It's very insightful.
Do you have whiteout?
So that would definitely work. Another thing you could do is you could just substitute your number back for the x. So you could do, for checking this one, I could do 4 to the 7. So substitute for x. Okay, and see if I get this number. So 4 to the 7, does it give me this number? I'm going to check. 4 to the 7, 16,384, and that's what I was supposed to get. 4 to the 7 is 16,384. So you can...
Put the answer as the exponent?
Yeah, so you can substitute it back for the x, which is the exponent, and see if you get what you're supposed to get out of it. Here, when you do 4 to the 5/2, you might need to put parentheses around that. So if I go back up here, it won't let me just do 5/2. Oh, it did, actually. Okay, so I didn't need parentheses. So 4 to the 5/2, and you get 32. So it worked. All right, I think we're ready to turn the page. So when you turn the page, it's going to ask you that question we had on the warm-up, which was, why is 10 a special number in our number system? We're going to be using 10 because log base 10 is special. When you see the button that just says log and it doesn't have a base, that means log base 10. And it's used so often that you don't write the base. It's called the common log. So if you just see log without a base, when you see log without a base, it means log base 10. Okay? But down here, I want you to write why 10 is a special number in our number system. You can use one of your ideas from your warm-up, or you can use one of the ideas that your classmates shared and I wrote on the board up there. Okay? Why is 10 a special number? All right. So when I type log, it means log base 10, so I don't have to put the base in. So right here, I can solve this problem by just taking the log of both sides because the base is 10. You only do that when your base is 10. This number is 100,000. These are going to cancel out. So I didn't put a base on it because when you don't put a base, it means log base 10. Notice the base of my exponential is 10, and so the base of my logarithm is 10. Now, when you just have log without a base written, you can just type that in Desmos. It's a little bit easier. You don't have to go into the functions.
So it's like the same thing, we're just not putting.
Yeah, you're just not writing the log, the base.
Okay.
So you do log, and then 100. Oops, I think I did a million. Yep, there's 100,000. So you do the log of 100,000. I'm getting 5. Can anybody confirm 5?
Yeah.
Good. Okay, so we get x equals 5. Do the next one. And remember, because the base is 10, you don't have to type the base. Ooh, shock. Okay. So I do the common log on both sides. Remember common log because 10 is a common number. And those cancel. And I get x equals -3. And I got that from the calculator. All right, let's look at 11. In 11 and 12, you're not being asked for the answer, so you don't even need to use Desmos. You just need to write out how you would find the answer. It's asking what will be the equation, okay? In 11, what is the base of the exponential? Which number is the base? I heard one answer over here. Can anybody confirm? Remember, the base is under the exponent. So in number 11, which of those numbers is the base? It's 5. Good. All right. So that means we're going to do a log base 5. So log base 5 of 5 to the x equals log base 5 of 6. These are going to cancel. So the x is by itself. This is what I would put in Desmos, but it's not asking for the answer. It just wants the equation. So my final answer, I'm simplifying the left side to x, and on the right side I'm just writing log base 5, 6. All right, try to do 12. Notice 12, the numbers are similar, but they're in a different place. That's going to change things. Try to do 12. Okay, in number 12, what's the base of the exponential? It's 6, thank you. It's because 6 is the number under the exponent. So now we're doing log base 6 on both sides. Log base 6, 6 to the x, equals log base 6 of 5.
And the 6's cancel?
On the left side, yep.
Yeah.
And we just get x. And then on the right side, we bring everything over. So if I wanted a number answer, I would put this in Desmos, but I don't need a number answer. I just need the equation. Okay, in 13, we're going to do the same thing we just did, but we don't have an x, and that's okay. Like I already know 6 to the 3 is 216. To rewrite that as a logarithm, I'm going to do the same steps. So I'm going to do log base 6 for this one. Log base 6, 6 to the 3 equals log base 6, 216. My log base 6's will cancel out, and so this one becomes 3 equals log base 6, 216. All right, now I want you guys to do B.
So the 3 is just like, it's not included, right?
So the 3 would not be typed into Desmos. If I wanted to check if this was true, I would type log base 6, 216 in Desmos, and I should get 3 as the answer. So a logarithm, the answer to a logarithm is the exponent. All right, do B right now. All right, so let's see if you did this right, guys. Levi says the base is 4, so we're going to do log base 4. 4 squared and log base 4 of 16. And these two cancel, and so you're going to just write 2 equals log base 4, 16. Okay, so we did a lot of equations where we just solved by taking the logarithm of each side. The next thing we're going to do is just a regression. You'll remember we have done other regressions. We've done like when we did our parabola project, we did a regression where you put points on your parabola and you found the equation of best fit. This is going to be a logarithmic regression. And so we're going to put these points in Desmos, and then we're going to use this equation down here to do the regression. So I need you to make a table and start putting these points in. I'm going to do the same thing, but don't try to copy the points from the screen. Instead, it's going to make sense to copy the points from the graph. All right, so the title of this graph is On the Move, and it's measuring the relationship between a city's population and the average pedestrian walking speed. So as the population goes up, what happens to the walking speed? Yeah, the walking speed's also going up, right? So we could create a logarithmic equation that matches this, and then we could predict the walking speed for a certain city based on their population. Okay, so most of you have these in your table now, and we're going to look at those points, and then we're going to put in this regression right here. So I put them in, but I can't see them. I'm going to press the zoom fit that's over here, the magnifying glass, and then you should be able to see them. Below here, I'm going to type the equation that's on my worksheet, y1 tilde a plus b log x1. All right, notice that there's no base on my log. When there's no base on the log, what is the base we're using? 10. Good. So that I'm using the common log, which is log base 10. If you scroll down, you can find your numbers for a and for b. And I'm going to round them to 3 decimal places this time because logarithms are the inverses of exponentials, and with exponentials, decimal places are very significant. So we need 3 decimal places here. You could do more, but don't do less. So I'm going to write on my paper that a equals 0.303. In just a second. I just want to write them. And then b equals 1.999. Yeah, we're going to write the equation, but I'll help you because I didn't give you a format for it yet.
I got something else. Maybe I typed it wrong.
It's possible there's a typo. Did you get all the decimal places? One thing that I missed the first time.
5 instead of 50.
Okay. All right, so to write the equation, instead of y1, we write y. And instead of tilde, we put equals. Then for the a, I'm going to put the a number, 0.303, plus, and instead of b, I'm going to put the b number, 1.999. Then log, and instead of x1, I just write x. Okay, so that's how my equation looks when I write it. And then we're going to do this next part together. So I need a recommendation for a city that we'd like to visit. You guys okay with New York? Okay. New York has a pretty big population, so that should be an interesting one to choose. So New York City, do a quick Google search and find me the population of New York City. I forgot to record that last part, so I'm going to say it again, but you guys can continue with just putting this in the calculator. So we chose New York City, we found the population, and we divided it by 1,000 because this is labeled population in thousands. And then we substituted this into our equation for x, and we're about to find how fast we have to walk in New York City.
8.50.
Okay, I'm going to also type it to see. We got 8.15. You can find your unit on the graph up here, feet per second. So that is faster than any of the walking speeds on the graph there. Look at the floor. Those floor tiles are 1 foot across. So if you look at the floor in our classroom, think about walking 8.15 of those, so just a little bit more than 8 of those every second. Like, I feel like I could do that in 1 second, but keeping that pace up would be really fast. All right.